So let's have a look at this problem that we started on Friday. Let's see if we can finish it up. So what we're looking at is designing the bolts for this bench. And this is page 415. We have to modify it just so slightly. We need to change when it says reaction. We'll change that word to resultant. Okay. And this isn't meant to be, what I'm doing is not meant to be quite so rigorous as some of the other stuff we do. I just want to just show you how you might use some of these things we're going through to solve problems, okay, that you might run into if you're working. That's my intent here, okay? So I'm not being quite as rigorous as I might be usually, okay? So let's have a look. So we're going to design the bolts in that bench. That's our goal here. So let's see how we might proceed with that. All right, the first thing I want to do is get the loads on there. So as we talked about, we're going to come up with a couple of loads. The first thing I'm going to do is over-design this because the bolts, one, they're pretty critical. We don't want them to break. And two, I don't think they influence the cost of this thing to a great amount. So I might be a little loose on this and way over-design them because it's not going to make the thing horribly more expensive. I'm not going to worry about that. So that's some of the things I think about with that. So what I want to come up with first are the loads. So I'm going to come up with the weight of the material that goes into the bench. Okay, so I'm going to take the volume of the bench, 0.26 meters, times the width of the bench, 1.8 meters, times the thickness of the bench. And then I'm going to look at that and realize it has kind of a mesh pattern on it. And I'm going to assume it has about 50% voids, 50% open space. So I'm going to take that volume and I'm going to multiply it by 0.5. And then I'm going to multiply that by the unit weight of the material the bench is made out of, which I believe is aluminum. So that's 28 kilonewtons per cubic meter. And I'm going to multiply those things together and I'm going to get 0.328 kilonewtons, which is 328 newtons for the bench. Okay, so what page are we on? 415, I think. Okay. Now for the load, I'm going to assume that there are three 300-pound people sitting on the end of the bench. So that's a total load of 900 pounds. And then I'm going to put a safety factor of 2 onto that, just because of that one photo I showed you where it looks like we might have some dynamic loading on some of those benches, okay? So that would encourage me to use a large safety factor again. So I'm going to use a safety factor of 2. I'm going to come up with 1,800 pounds for that design load. Okay, then I'm going to convert that into newtons, and I just took that out and said it's about 8,000 newtons. That's about as far as we got on Friday. So we good with that? So what we have now are 2 loads. What's called the dead load, which is the load that doesn't move. That's often the weight of the structure. That's the weight of the bench. And then we have the live load, which is the stuff that moves around, and that's the people. Okay? So the next thing I'm going to do is I'm going to draw up a free body diagram, a force diagram of what's happening. That's the next thing I'm going to do. Okay, so there you go. I'm going to have the 8,000 newtons at the end of the bench and the weight I'm putting in the middle of the bench. Now those brackets I'm going to kind of ignore. I'm not going to come up with a full center of gravity of this thing. The weight I'm applying it where I assume the centroid of the bench is, and I'm going to put that in the middle of the main body of the bench. So I'm going to kind of ignore that bit when I find the centroid, the center of gravity where I would apply the weight of the bench to, okay? Now notice that once again, I'm kind of making assumptions that are on the safe side. because if I include that little armature on my center of gravity calculation, which way will that pull my center of gravity, to the right or the left? If I include that little bracket on my center of gravity calculation. To the right, correct? That would put the load there, which would have less of a moment arm, which would create less of a couple at the bolts, right? So I'm kind of getting into a little more working world mentality, okay? Rather than screwing around with taking it out to 12 decimal places, I'm making quick assumptions that are on the safe side, is what I'm doing. And I'm doing this because they're bolts. I don't want to spend 8 hours analyzing bolts, okay? Because they don't influence the cost that much. And see, when you work, the cost is a big part of what you're thinking about. Okay, you want something safe, but that has a reasonable cost. Okay, so I'm just using for the center of gravity where I will apply that weight. I'm just using the bench. I'm not worrying about the brackets because that's going to complicate things. Okay, we good with that? So what I want to do now is I want to come up with the resultant, because that's going to influence how I design the bolts. So the resultant will be sum of Fy, and that should be pretty straightforward, shouldn't it? Minus 8,000 newtons, minus 328 newtons. This is just not working for me today. I don't know. I have to tell my boss that I need a bigger computer. This is just too small for my hands. Okay, so what we get is negative 8328 newtons. Okay. So that's the sum of Fy. Okay. Now I also want to take moments about this point. Let's call this point A. So or will I call it point A? Just give me a second here to see what I called it last time through. Did I call it A? I called it C, so I'll call it C again. Sorry about that. So we'll call this A, we'll call this B, and C, okay? So then I'm going to take moments about C. And what am I going to have there? I'm going to have 8,000 newtons times 0.43 meters. Now to get 0.43 meters, what I'm doing is I'm adding 0.26 and 0.17. That's where that moment arm comes from. Now again, see, I put my people at the end of the bench. I did that to maximize the moment arm to get me the safest answer. That's going to get the biggest moment at the bolts. That's why I purposely did that. My friend's an architect. He was designing a porch once, and we were talking about the deflection of the porch. Overlooked the Pacific Ocean, in California. And I said, okay, let's assume we got a big barbecue and all the people on the porch on the rail looking out at the ocean, because that'll get us the biggest moment. That will get us the safest calculation on the deflection. Okay, so that's what I'm thinking about here. Okay. So I've got that, and then I'm going to have also the weight of the bench. So we good with that, what we're up to? Okay, so again, we're not going 12 decimal places here, but we're making safe assumptions. We're ballparking a little bit, but we're doing it, we're always picking the safest assumption, or the assumption that will get the biggest load that we're going to design for. That's how we're doing this, okay? All right, and what else do we got? We got 328 newtons. Yeah, that'll be times 0.3 meters. Now where that comes from is 0.7 plus half of 0.26, because that's where I'm applying that weight in the middle of the bench, half of 0.26, okay? I'm going to add those up, and I'm going to get sum of MC. All right. And that comes out to be 3,538 Newton meters. So now what I have is a resultant, don't I, right there. So what's happening at those bolts is I've got a downward force of 8,328 newtons, and I've got a couple pulling around like that, and that is 3,538 Newton meters. All right. So are we doing all right with that? So we good? Okay. Now, that's what we got going on. Now, what is that downward force going to do? What's the action that's going to bring down on those poor bolts?
Shear.
It's shear. It's going to try and shear them off at the wall, right? And what is that moment going to do to those poor bolts? Torque. What's the action that the bolts are going to feel on account of that moment? What's it going to try and do? And if you're talking to someone who's pouring the concrete, what are you going to tell them? What is that going to do to the bolts? Pull them out. Yeah. Okay. Good. Exactly. Yeah. It's going to try and pull them out of the top, right? And it's going to happen at the top primarily, right? Okay. Good. Okay. So that's what we're thinking about. All right. So now here's how we're going to go through this. We're going to take the 8.328 newtons. But we got two brackets, right? So I think that's going to get 4164 newtons per bracket. Now we got 4164 newtons per bracket, but how many bolts do we got in the bracket? 4. So we might divide that by 4, and we're going to come up with about 1041 newtons per bolt. Now, if that bracket, if those bolts aren't perfectly aligned, there might be a little more force on one bolt than another, but we've already thrown our safety factor in there, okay? Now, if we're really worried about it, maybe I'd jack that number up a little bit again. I don't know, but you know what I'm saying? If those bolts aren't perfectly placed, the load on them will be a little bit uneven, okay? But let's just use that number. That's the shear strength I want on the bolts, okay? About 1,000 newtons per bolt. Okay, because what that's going to try and do, if I've got my wall here and I got that bolt, that force is going like that, and there's going to be a reactive force like that, and that's going to try and shear those things off. That's what it's going to try and do right at the wall, okay? All right. Now, what else I got going on here is I've got 3538 Newton meters, but again, I've got two brackets. So that's going to be 1769 Newton meters per bracket. Okay. And then I've got two bolt pairs, right? Y'all know what I mean by that? Because what's going to happen is I'm going to get kind of a couple like that. It's going to affect a pair of bolts like that. Okay. So now I've got 885 Newton meters per bolt pair, I'll call it. Not, just making that up, that word. Okay. You good with that? So now we got that. Now let's have a look at that bracket a little bit. We're going to have to make one big simplifying assumption. I'm sorry about that, but I think we will. So let's see what we got. Everybody keeping up? Everyone doing all right? Okay, now let's not worry about that little extension down. That's going to complicate things, and it's going to get away from the model of a couple that we're kind of been working with. So let's kind of assume the brackets like that there isn't much distance between the bolts and the bottom of the bracket. Okay. So if we were to make that assumption there, here's our bracket. There's this bolt. Let's see. When we have this couple that's applied, the 885 Newton meters, what that's going to try and do is pull this bolt out, right? This bolt would be pushed in essentially. That's essentially turning into a couple. So over here I have a pure moment. I'm going to have two forces there, one out and one in, that translates to at the bracket, and the distance on the brackets is 0.2 meters. So I'm going to have F bolt and F bolt So I'm going to have 885 Newton meters. And that's going to equal that basic couple thing that we do, the force times the offset distance. So what I'm going to get trying to pull that top bolt out would be 885 divided by 0.2 meters, 4423 newtons. That's what's trying to pull the bolt out of the wall there. Okay. So that's the basics of how we might use a resultant to do some practical things, to design the bolts and to design how they're embedded into the wall. Because there are formulas I know for concrete and embedment lengths that you can look at, though I've not used them for a long time. Okay. Now what if that number is too high? Let's say we can only handle 3,000 newtons for that bolt. That's all we want to deal with. What adjustments might we make?
Put grade 8 in there instead of grade 5.
Okay, yeah, use a stronger bolt, but
more bolts, longer bolts.
More bolts, longer bolts. How about the bracket?
Make it thicker.
You could make the distance between the bolts.
There you go, longer bracket.
Yeah.
Okay, that might work.
Because
Okay,
that would be a smaller multiplier for.
that might be a cheaper solution. Okay, it needs more room though. Okay, but
But if you
might work.
make the distance bigger, you might as well throw another set of bolts on there.
Okay, we'll call it good.
One more bolt.
Okay. Yeah, there's lots of ways to fix that problem. Okay, but the other thing I just want to get across is sometimes when you're working, this is how you might approach it. Okay, you just make safe assumptions every step. You over design because it's not worth your while to get an exact model of that. Okay. So we doing all right with that? Questions? Okay. All right. There you go. So we will take objects like that and turn them into free body diagrams or force diagrams. So here's how we do that. Okay. We decide what we want our object to be. We draw a boundary around it. And then we put the forces acting on it and the couples now, because we're getting a little bit further down the road than we did when we were just looking at points in space that we're doing equilibrium for. Okay, so and there's two types of forces that act and two types of couples that act. There's contact forces caused by physical contact and body forces caused by force fields, things like gravity. Okay, and I'm on page 360 is where I am. Okay, supports exert forces on objects. These support forces are called reactions. Okay. Okay, the reactions caused by a support correspond to the motion that the support prevents. Okay. Generally speaking, reactions can be assumed to act in either of two directions. Okay. If you get an incorrect assumption of direction, you'll just lead to a negative answer. So it's no big deal. If you get a negative answer, it just means you assumed the wrong of the two possible directions. You just have to turn the force around is all. Okay. We apply weights at the center of gravity. Okay, so to model reaction supports, which is what we're going to do here, we look at the motions that the support prevents. Reaction forces and moments are required to prevent motion. Okay. So we've gone over a couple of these, but first one would be a cable. So I'm on this table there on page 360. A cable, the force acts in the same direction as the cable and the force pulls on the object. So if I'm modeling how that cable affects that rod there, it will pull up and to the left. If I'm modeling the support on the top, the cable would pull down and to the right. In either case, the cable is pulling, all right? So that's a one directional reaction, acts right on the line of the cable and it pulls. Okay. So cables can only pull, they can't push. So there's a cable. So if I'm going to model how this weight at the bottom is being handled by the cable, I would put those cable forces on like that, right along the line of the cable and pulling is what I would do. If I'm modeling how they affect the boom on the crane, they would pull back the other direction. Okay. Okay, there's cables that are being used to keep that pole in equilibrium so that it doesn't fall over. See that nice little trick there where they kind of use this to get their angle pulling out, then they put this little strut in here so they can turn that force down and keep it inside the fence. Okay. If I'm modeling the top of that telephone pole or power pole, I think it's a power pole, what I have are forces going like that. Okay. There's a cable holding up an awning, kind of pulling it back like that to keep it from sagging down. Okay. Sometimes they'll put turnbuckles in these cables so they can keep tightening them up as the signs start to fall and sag a little bit. So the forces would go like that. Okay, the next type of force is a linkage. A linkage is a little strut that has two holes in it and two pins. The force acts between the pins is what it does. The force in the link acts from one pin to the other. The force can now push or pull. Links are called two-force members because they have two pins, two places where the forces can be applied. We'll get into these a lot more down the road when we look at trusses. Okay, so that's a linkage. There's a link. Okay. Good with that? Okay, we have three things that are all kind of similar. There's rollers, which have wheels on the bottom. There's rockers that kind of have a section of a wheel, kind of an arc section there, and smooth surfaces. They all act somewhat the same. The force is normal to the surface on which the roller rests. So that would account for rollers, rockers, and also smooth surfaces. There's a smooth surface. Even though that broom handle is angled, the force on it is normal to the floor, going up, if I assume that's all smooth. Now that's an assumption, nothing's perfectly smooth, but as we were just kind of going over, sometimes you make assumptions that make your analysis cleaner and you overestimate the forces. That's a common way to deal with things, okay? So that force would be up. There's a roller. Okay, there's four rollers. The force on the rollers would be up. Okay, like that. If the roller's on an inclined surface, the force is normal to the surface. Like that. Okay. That's an old drapery rod. They don't make drapes like that very much. How would you model that? How would the force of the reaction be exerted on that?
Roller on the inside of that track.
Yeah, it's a roller that can't move either direction. So you'll notice that there's no resistance left and right. The only resistance is up or down. Okay, good with that? There's a 3D roller, okay? So we've been looking at two-dimensional ones. There's one in 3D. Force is normal to the floor. It can roll any direction, left, right, in and out of the page, but it can't move down, so that force is required to prevent it from doing that. That's the force of the floor on the roller. What's that?
Normal force.
Normal, yeah. Okay. Okay, we have sliding collars, which are kind of unusual. The next big one that we have are pin joints. Okay, pin joints, you have a pin of some type, a bolt or a rivet, or just a smooth pin that fits through a hole, a couple of holes, and attaches that rod to the connection. It's called a pin joint. Now, pin joints will not allow movement in either direction, left, right, or up, down. So we model those with two reactive forces that are perpendicular to each other. We can use inclined forces or in the straight XY directions. Okay. Sliding collars are like rollers. The force is normal to the shaft. So the thing is free to move this direction. So the force is normal to the shaft, okay? Like that. So the force is what prevents the motion. So for pin joints there, here are these struts holding up the roof of the Salem Convention Center. You can see the pin joint there. So I would model those with two forces that are normal to one another. Like that. Okay. Now I'm assuming those are frictionless. They're probably not, but again, I model them as though they're frictionless because I can handle a model like that. When I start throwing in every possibility of what it's doing, the analysis becomes too complicated, okay? So I would assume they're frictionless, design it, and throw in a little safety factor is what I would do. Okay. There's a pin joint right there on a bridge, commonly used on truss bridges like this. See any pin joints? It's a piston. How many we got? What's it? We got one there, right? There's a rod that goes through the piston and joins that to the connecting rod. How about right down there? It fits around the crankshaft there. Okay. So those are two pin joints there. A ball joint is like a three-dimensional pin joint. It allows the top object to rotate around. So there you see the ball and socket, they're sometimes called. I think you're all walking around with a ball joint in your hip. Probably got two of them, okay? So you got a socket in the hip, the pelvis, I guess you call it, and the hip kind of runs into that, okay? Trailer hitch is a ball joint, okay? So it's meant to allow the trailer to rotate a little bit while you're pulling it up along the road, okay? There's a universal joint, kind of like a ball joint, meant to allow rotations in all different directions, like that and like that. Okay. You might have a couple joints like that in your car if you get under there and look. Okay. Okay, from there we go to fixed supports and fixed connections on collars. Fixed connection on a collar, the force again is normal to the shaft. There's also a moment reaction now. If that's all fixed, this shaft here can't rotate. So to prevent rotation, there's a moment reaction of some type. A totally fixed support is when, like that bracket we were just looking at, it won't allow motion up, down, left, right, nor will it allow rotation. So two force reactions and a moment reaction. That's what you get in fixed supports. There's a fixed support. See that pole is welded to the plate. The plate is bolted into a concrete pillar. That thing's not going anywhere, okay? Not going left, right, not going into the page out. It's not rotating. So that's a fixed support. That's a fixed support, okay? That roof is not supposed to go anywhere. And they got an extra cable in there just to make sure it doesn't, I think. All right. But you see, why did they do that, okay? Because those are football stands, right? People want to be able to see. They don't want posts down here. So that's called a cantilever is the term for that. Okay. There's, I think, the biggest cantilever building roof, at least at its time, in the world, I think. It's a horse track, a racetrack for horses. Okay. So that just extends out from the support. So you could analyze that like a fixed support right where I'm drawing. Okay. There it is on the inside. Okay. All right, so that's just to run through some of these supports. Let's look at a few situations here and how we would draw free body diagrams, okay, of objects. So let's say we've got a bracket like that. We want to get used to the symbols that are used. Here we have a triangle with hatches on the back and a pin up there. What is that? Pin joint? What do we got at B? That's a roller, yeah. Okay. Now why don't you draw up a free body diagram of that bracket? Turn all those different objects, the weight of the bracket, the 110-pound weight, the pin joint, and the roller, replace those with forces. You see that? I think that's where that free body part of that word comes from, that phrase comes from. You're freeing the object from some of those constraints and you're replacing the constraints with forces. If you got questions, you let me know. All right, something like that. You draw the boundary around the bracket. Okay, the pin joint gets two forces. Usually I use R for reaction, RAX, RAY. Got a force normal to the ramp. The ramp is 67 degrees. So what I end up with then, I want that angle on the force. So what I've got is a situation like that. Being as the force is normal to the ramp, that's a right angle, and that's 67. So I got 180 degrees in a triangle. I'm going to take away 90, and I'm going to take away 67, and I'm going to end up with 23 degrees right there. The short way to get these is just to take 90 minus the ramp angle, and you get the angle of the force, because you've always got 180 minus the 90 for the right angle. So that RB goes up right at 23 degrees. We got 40 pounds at the center of gravity and 110 pounds at the hanging weight. So there's the free body diagram. We doing all right with that one? We got any questions on that? Okay.
RB like the normal?
RB is normal to the ramp. The ramp is the flat surface, and RB is normal to it.
So the wheel isn't
The wheel is exerting a force on the ramp, but we're finding a free body diagram of the bracket. So we're looking at what is happening to the bracket, not to the ramp. So the force on the ramp on the wheel goes through that pin and is exerted on the bracket from there.
Is the bracket the whole thing?
Yeah, the bracket is what we're analyzing. So you kind of pick what you're analyzing and focus on it. Okay. good with that? Okay. How about pulling a crate up a ramp? Now what I would do on this one is I would set up an axis system in line with the ramp. I'd set up the axis system like that because I'm going to have friction acting on this thing. I've got the 600 Newton force at an angle that's aligned with the ramp, so I would tend to set up an axis system as shown. Look at the weight of that thing and see, you're going to need to convert that mass into a weight. We do statics with weights, not masses. And look at the angle the weight would make with the ramp, because or maybe more properly with the y prime axis, because that weight acts straight down. As far as that crate's going, probably something like that. Now I've got the how these. Oh, whoops! I forgot one thing there, didn't I? Yeah. So that's often called the normal force. There's the friction. There's 600 newtons, and this is the weight. 70 kilograms times 9.81 meters per second squared, which is the force, or excuse me, acceleration due to gravity.
You would want like 600 sine 20 in line with the normal force and 600 sine 20 in line with the x-axis from my Freebody diagram?
That's kind of optional. I tend to, personally, I do that when I write up the equations, but you could do it that way too. I mean, it isn't like my way is, you know, the way to do it. It's kind of, that's just how I do it. But yeah, you could do it that way for sure. So you could break up the 600 newtons into components and put it on there. Right, now the one thing I want though is I do want the angles on here, and I want those ready to go. So the force of friction, the normal, the 600 newtons, I already know that 20-degree angle, and then I've got the 687 newtons. That's the one that I need to figure out the angle on. So what's the angle there? And why don't we write it up like this? What's the angle right there for that 687? I'm sorry now?
Minus 17?
That's going to be 17 right there. So that'll be 17 degrees right here. Okay. So that 687 will make a 17-degree angle with a line normal to the ramp. Okay, to find 17, there's different ways to do that. Let's see, what we have here, let's draw up a sketch. We've got 17 degrees for the ramp.
Oh.
That's pointing straight down like that. And then if I extend this out and put a normal in here, and I'm just kind of trying to figure this out. There we go, that would be 90. this would be 73. So yeah, we could work into that 17. That little vertex angle there is 17. Okay. We'll finish these up Friday. We'll probably, now, did I assign a couple of those problems? We got just a couple minutes here. Let's look at 241 and 2. Those are going to be due on Friday, I think.
Yeah, 241 and 42.
Now, let's just look at one of those real quick. So Friday is the 7th, is that right? I think so. Now, 241 is on page 11A. And then 242 is on page 11B. You're finding resultants there. Now on 11A, that's a two-step process. The top, part 1, just find the resultant. But I also would like you to do part 2, which is to tell me how do we get from that diagram to, how do we get from the actual situation there, a concrete slab with a beam underneath it and sand on it, how do we get from there to the diagram? So that's what I want you to derive in part 2, is how to get from that sketch that I'm showing you in part 2 to the diagram up above. Okay, so that's what we've got there. That's what I'm looking for on that, just to clarify that. We can go over that on Wednesday a little bit after the test. So remember, on Wednesday we'll start with the test till 4:15, and we'll just take a little bit of a break, 5 minutes or so, and then we'll just cover a little bit of new material too. All right. All right, so we're good to go?
Did you say 4?